Hi there, welcome back. And in this video lesson we're going to look at satellite motion. Now, we've done a little bit of satellite motion before in the National 5 course. At the very end we would have talked about Newton's thought experiment and the premise that a satellite in orbit above an object, a planet for example, is just really, it has a constant horizontal velocity and it's in constant free fall. And this still holds true, but what we're going to do, we're just going to take this on a step further. And for the first time, now we have the tools that can allow us to analyse this in a lot more depth. Before we didn't have the maths available or the physics knowledge available to us. But now with our knowledge of rotational motion, we'll see that that satellite motion fits perfectly for what we've been doing earlier on in the mechanics course about rotational motion. And so, well, let's go over to the learning outcomes and we'll see what we need to know for this. Picking straight back up from where we left off, we got through the first 5 in an earlier lesson. We finished with Newton's inverse square law of gravitation and gravitational fields. But now looking at 4.6 and 4.7, it's saying I can use appropriate relationships to carry out calculations involving period of satellites. Now that comes first because this is the most common question to be asked is to work with periods of satellites. We're also looking at masses, orbit radius, satellite speed, and that. And then 4.7 below, it lists all of the formulas that we could use for that. And now, looking at the list, you'll none of this is new. The first one there is obviously Newton's inverse square law of gravitation, but then this one and this one, this is just describing centripetal force. And then from that point, we're having the fact that omega here, which is angular velocity, can be defined for one entire revolution, 2 pi radians for one complete circle, and obviously the period of the satellite. But we'll talk about that more as we're going through this. So if we remember back to our National 5 definition of what satellite motion was, is that, well, we started off with a kind of thought experiment that if we threw an object, if I was standing in a field or a park and I threw a ball, it would move in a sort of projectile path, and if I threw it harder, it would move in the same projectile path, but just have a further range. And the defining feature of a projectile would be that during its flight, it's going to have a constant acceleration. So it's going to accelerate due to gravity on the surface of the Earth. That would have been 9.8 meters per second squared, and also that it will have a constant horizontal velocity. So VH equals constant. And again, we developed this then further and higher. We looked at projectile motion in a lot more depth. But there's obviously a problem here, and one that we've conveniently completely ignored up until now. In fact, we're still going to ignore it, and that was the fact that the horizontal velocity was going to remain constant. In fact, that we do all of this in a vacuum. The acceleration due to gravity is going to remain at 9.8. It's not going to ever reach terminal velocity. It's never going to slow down from its horizontal component velocity. And this is because on the planet Earth we have an atmosphere. But when you actually start to take these into space, then there is no air, it's in a vacuum, and so the horizontal velocity will actually remain constant, and the satellite will never reach terminal velocity. Okay, so anyway, back to our kind of thought experiment, that if we had this, if we threw it harder, and if we kept sort of increasing the I guess the horizontal launch velocity, to a certain extent we would have, so if this is us standing somewhere around here in Scotland, we'd probably be a wee bit lower. This is a bit high, but and the fact that we're actually massive. I'm worrying about the scale of the drawing when it is ridiculous. I'm standing on a stellar pebble, and so if I was to throw my ball even further, it's still going to follow this projectile path, but just now, if we throw it hard enough, we're starting to get the curvature of the Earth into play. So if I were to continue this and throw it, but if I were to throw it at just the right speed, horizontally, then it's going to travel far enough that its horizontal motion will be constant, obviously, but as it accelerates down towards the surface of the Earth, it'll bend down. But if it's moving sufficiently fast horizontally, the bend that's caused by the acceleration towards the center of the object, the center of the Earth in this case, will make it move in a circular path. And this is exactly what satellite motion is. There's, as I said before, there's no atmosphere in space, and so we will have a constant horizontal velocity. The acceleration due to gravity. Now, I've said it's 9.8 there. It will not be 9.8 in space, and it's not because you're weightless. You're not actually weightless. If a satellite was truly weightless, it would not be able to be in orbit. And so, I guess if we're looking at a sort of typical satellite orbit, then we would have well, the ISS, I think is about 89% of gravity of Earth. So whatever 89% of 9.8 is, that's the gravitational field strength on the ISS. Another time about why astronauts float around and they have apparent weightlessness, but I'm not going to get into that just now. That's a conversation for another time. So, as it's moving in this circular path, we're having a constant horizontal velocity, and really what we would know this as, I guess, if I actually just, I'm going to just do it. So, me, mass of the Earth. We can have the radius, the distance from the center of the Earth that this satellite is in orbit. Now, from what I'm talking about up here, it has its constant horizontal velocity, but what we'll call this actually is, we call this now tangential velocity, and this is v. If it has tangential velocity, it's moving in a circle. It will also have angular velocity, which is omega. Now, what causes it to move in the circular path is that at any given time, so just say here, any given time, it will have a constant force being applied to it, which is attracting it, or constant force is being applied towards the center of the planet or of the object, which is exactly what the conditions for circular motion are, and indeed this force is centripetal force. And so if we start there, we can say that force due to gravity is going to be equal to the force, the centripetal force, and then so the force of gravity is obviously, engage the brain, so ME M over R squared, And if we equate this to central force, we're going to have v squared over r. And so this is a crucial starting point. As I say, you're asked many wonderful things with long algebraic manipulations throughout this, and every time this is going to be your starting point. So let's have a wee look and see what we can do with this. Well, the first thing is that we could work out the velocity of a satellite. So if a satellite is in orbit, we could, from known values, we could work out what the velocity of that would be. So we'll start off with here as ever, and I'm going to take this in sort of quite slow steps. I'll show all of the steps, and I'll try to cut out as many shortcuts as I possibly can. So well, let's just say velocity of satellite, and so we'll start with a g mm over r squared equals mv squared over r. Cancel out m's, cancel out the square from there. Now this, if we're just looking for velocity, then this is our subject here, v, and so we'll just leave v where it is, cross multiply with the r. Sorry, there we go, my r is already gone, and so we're just left with v squared, and so v would be g m over r. And so you have a constant here, and then you've got the mass of the planet, or whatever object is, whatever object the satellite is orbiting, and the radius, i.e. the distance from the centre of that object. That's better, I've composed myself a wee bit and now engaged the brain again. So yeah, the velocity of the satellite has absolutely nothing to do with the mass of the satellite. It could be anything. It's purely dependent on the mass of the planet that's orbiting and the distance from the centre of that object. If it goes faster, if you increase the speed of it, then you're going to change the radius, obviously. Okay, so we've got velocity of a satellite. What else can we do? Well, we can find the period of the satellite, and so we'll do that next. Period. Oops, still learning how to spell satellite, so bear with me. Period of satellite, and again we'll start with the standard equation, g mm over r squared is equal to mv squared over r. But this time I'm going to introduce a couple of new equations. Well, not new equations, but that would be that the tangential velocity of the satellite is equal to the radius times the angular velocity of the satellite. And also we know that from circular motion, if it makes one complete revolution, it's going to have an angular displacement of 2 pi radians, and then the definition of period is the time for one revolution, and so that would happen in a time of big T, which is period. And so these two equations can be substituted into here, and then we will get, and we'll solve for T. Again, we can cut out the masses, get rid of this and this. And so we're left with Gm over R, and that's going to equal V squared, but in this case we're going to substitute R omega. So it's going to be all squared. Then what we're going to do, we're just going to substitute omega for this here. squared, and just square out the brackets. So we would have 4 pi squared times r squared divided by t squared. And then we'll rearrange for t squared. Giving us this. Now, we could go further. If we wanted to find period, we would just take the square root of this here. But this is significant here, and I'm going to leave it at the moment just here, because 4 pi squared and g are obviously constant, and if we're looking at how the height of a satellite or the radius of the satellite's orbit is affected, mass is constant, so the mass of the planet does not change, and so really what you have is you have these, this is a constant value, and so what we would have from this is that t squared would end up being directly proportional to the cube of the radius. And this is known as Kepler's third law of planetary motion, or Kepler's third law. Back in just at the start of the 17th century, 16 something, Kepler came up with his 3 laws of planetary motion. Paraphrasing very briefly, the first law would be that the planets move in elliptical orbits rather than the previous held belief that the planets moved in circular orbits. And so the planets move in elliptical orbits. I think the second law was that the arc swept out by the area of the arc swept out by the planet for any given period of time is constant, and so obviously, well, if you're having the sun being in here and it's moving in an ellipse like so, then if we were to look at a similar period of time and work out the area that the planets are going to move, that's going to be constant for the same period of time. It's going to move this as it's going to move to this. Obviously this means that as it's working its way through this segment of its orbit, it's moving faster than this portion here, and so that it will speed up as it's coming around here. It's going to be moving slower at this point, and so that was his second law, and his third law is that the square of the period is directly proportional to the cube of the radius. Now you have to know nothing about Kepler's laws for advanced higher physics. You saw the learning intentions at the start of this lesson, and you have to be able to equate our gravitational force and our central force, these 2 equations, and from that point on you can just do that. So if you wanted to finally to get period, we would just take the square root of this. It's not 4, it's not 2, it's mumbling now, r cubed or gm. And so that would be the period of a satellite. You have this in your course notes, so you have the satellite motion, velocity, or rearrangement for period, and then here we just go a little bit further. We work out the actual value of this constant value. On the next page, there's just a little worked example of where you can use the period squared over the radius squared equaling a constant value, and you can calculate you can verify that actually that is a constant value for each different celestial object. Okay, so a question, how heavy is the Earth? How do we know what the mass of our Earth is? We send somebody down to Australia and stick a set of bathroom scales, really big, specially made bathroom scales that the Earth fits on, and we sit and we weigh the Earth. Well, of course not. But we can use the physics that we now have to figure this out. And to figure this out, well, we need two things. So here we have the Earth. So we need an object that is in orbit around us, so around the Earth. And it just so happens that an object that's always been there, I say always, it's always been there when I've looked up, but that is the Moon. So we have our Moon, and we need to know the distance. So we need to know how far that is away from us. So it's orbital radius. How do we know that? Well, I guess the easy way to say how we know that is, well, when we went to the Moon, we stuck some mirrors on the Moon, and now we can shine some lasers, and we measure the time that it takes for the laser light to go from the Earth to the Moon and back, and we divide it by 2, and we've got the speed distance time. Actually, it was the Greeks, the ancient Greeks, that first did this. Is that they stood in 2 places during a lunar eclipse. So as the Moon passed in front of the Sun, there was a total eclipse in one of the places, and a partial eclipse in another place where they were, and they used parallax to find the distance, which is pretty awesome. And so anyway, we know the distance between the Earth and what am I saying? We know the distance between the Earth and the Moon. The next thing we need to know is the period, how long it takes for the Moon to make one complete revolution of the Earth. And well, we do know that that's what's called a month. So you're going to look at this and you're going to, wait a minute, that's not a month. But if we take the average time that it takes for the Moon to make one full cycle, one full circle around, then we'll have that. I don't know who came up with 30 days, sometimes 31 days, 28 days, or maybe 29 days if they're feeling a bit lucky. Who knows? Maybe somebody can tell me the history of months and why we have stupid months, because surely a month should be the time it takes for the Moon to go around. I don't know. But anyway, it takes 27.3 days on average for the Moon to make one complete revolution about the Earth. So now we have everything we need. We've got the radius between the Earth and the Moon. We have the well, hang on, let's go to our appendix. Mean radius of Moon orbit. As I'm reading this from my data sheet, it's 3.84 times 10 to the 8. 3.84 times 10 to the power of 8 meters. So we have our radius, we have our period, and now do we have the physics? So we're going to equate C Okay, and again, as before, we'll cancel out masses and take out this. So we are going to just follow all the way through again until we get to, with obviously we have our period, we have our radius, and so we'll just carry on. Now remember v squared equals r omega, and omega is 2 pi over t, so we're going to have 2 pi over t multiplied by r, and all of that's going to be squared. And multiply out the brackets. 4 pi squared r squared over t squared, cross multiply, and in this case we're looking for mass, so we're looking for the mass, which in this case is going to be our mass of the Earth. So leave ME there, we're going to have 4 pi r cubed all over g t squared. Oops, sorry, I'll drop my square there. So 4 pi squared times times 10 to the power of 8 cubed over Newton's gravitational constant 6.67 times 10 to the minus 11 times the period squared, so that's 27.3 times 24 times 60 times 60, and don't forget to square it. Okay, so we've entered in the calculator and we get 6.02 times 10 to the 24 kilograms. Which is what it says in the data sheet, so it must be true. Okay, and we could do this for the Sun. Indeed, there's a similar calculation from the course notes done with the Sun, and we get the mass of the Sun by using the distance between the Sun and the Earth, and the period of orbit is 1 year. Well, there's another wee example there, which we can look at. This is going back to the first equation that we derived for the velocity of a satellite. So how fast is the moon travelling relative to the Earth, and we get 1021 meters per second. So the final thing that we're going to do today is we're going to look at the special case of satellites that are geostationary satellites. Well, if we again remember back to our National 5 physics, when we were talking about geostationary satellites, we defined them as satellites that, well, they stay in a fixed point above a certain place of the Earth. They will have a period of 24 hours and they'll orbit at an altitude of 36,000 kilometers. Now, what we're going to do, we'll go and derive an equation for the radius of a satellite for it to be geostationary, and we'll see that every value must be or is a constant value, and so the radius is fixed, and the radius can't actually is fixed. For it to be geostationary, it must be at a certain altitude or a certain height above the Earth. So again, as before, we're going to start by just equating our forces. we're going to put in our so V equals R omega, and omega equals 2 pi over T. And this time we're going to rearrange for R. And so bring the two R's down there, we're going to get, that'll give us R cubed. So if I just get R there, get rid of them from there. So we want to find what R is. And so I'm just going to flip both sides of the equation. I'm going to be left with R cubed. GM would then go down to the bottom. But when we cross multiply, so we're going to have GM T squared, and that's going to be over 4 pi squared. Okay, and now at this point, if it's geostationary, what it means is we want it one orbit to take 24 hours. And I don't know if you will remember this, that for it to be properly geostationary, it must be orbiting above the Earth's equator. It's very difficult to show on a piece of paper like this, but if this is the equator of the Earth and the satellite is, say, up here, as the Earth is spinning around in this direction, as the Earth is spinning around, the satellite is also going to be moving around in that direction. And if it takes, say, this point 24 hours to make one full revolution, we need this to take 24 hours to make that one full revolution. And so the distance for that to happen, that's what we're looking for. Now if it's 24 hours, then G is a constant, M, the mass of the Earth, is going to be a constant, and T is now a constant. And so you can see that every single term in this equation is going to be a constant, and if that's all constant, then the radius must be a constant value. So the cube root of GMT squared over 4 pi squared. So let's put our values in there. That's our sort of final derived formula. So G 6.67 times 10 to the minus 11 times mass of the Earth. Well, we know that now. So 6 times 10 to the 24 times the period, well, it's 24 hours, times 60 times 60 for the number of seconds in one day, and that would be all squared, all over 4 pi squared, and then we have the cube root of that. Right, I'll be back in a minute when I type this in. Okay, so typed in, let's see if the calculator needs some thinking time to get this done. A little bit of thinking time there. And so what do we have? Well, we've got 42 times, so okay, let's deal with one thing at a time. So we'll have 4.23 times 10 to the power of 7 meters. Now, okay, well that's not what you were told at National 5. At National 5 we were told that a geostationary satellite must have an altitude of 36,000 kilometers. That's not even 36,000. There we go, 36,000 kilometers. Now, if we look at 36,000 kilometers, we're really talking about 36,000 meters, or 3.6 times 10 to the power of 7 meters. Okay, so the difference in the two answers, I hope you've figured this out already. I hope you're saying that, Mr. Garrett, this is the radius from the center of the Earth and not the orbital altitude, not the height. And so we need to subtract off of the radius of the Earth, and I'm hoping then that we'll get 3.6 times 10 to the power of 7 meters. So radius of the Earth, 6.4 times 10 to the power of 6. Therefore, we can say altitude is equal to 4.23 times 10 to the power of 7 minus 6.4 times 10 to the power of 6. Oh, you can't see a thing. Close enough. 3.6 times 10 to the power of 7 meters. And so there we have the altitude of a geostationary satellite, and we now know that it must be that altitude, because if it's not that altitude, then it's not going to have a period of 24 hours and it will not be a geostationary satellite. So thank you, physics, for giving us satellite television and lots of other things which are useful. Alright, well, that's everything that we have on satellite motion. There will be subsequent lessons talking or going through this further, but in the meantime, there will be an assignment coming to you from the P&N problems book, dealing with, first of all, Newton's inverse square law of gravitation, gravitational fields, and then satellite motion as well. So I hope you have fun with that. But anyway, thanks for watching for now, and I'll see you again soon. Okay, bye.